Today, I want us to start our discussion on differentiation from the first principle. But before we look at differentiation from the first principle, let's look at gradients of line joining 2 points. So let's assume I have my points P, which is x sub 1, y sub 1, or x1, y1. Then another point Q, which is also x2, y2. Okay. Now, the gradients of the line joining these 2 points, we have, let's that be M. Let's assume we have this line drawn here. So P, x1, y1, and then Q, x2, y2. Okay, so let's find the gradients or the slope of this line. Okay, so when I said let the slope be represented by the letter M, and in that case, let me trace this to this point, y1, and then here becomes, y2. Then this becomes x1, and then with this one, x2. Okay. So then this implies the gradients of the line joining these points. I said it's supposed to be M, and that is going to be y1 minus y2 over x1 minus x2. It can also be y2 minus y1 over x2 minus x1. So please, it's either y1 minus y2 over x1 minus x2 or y2 minus y1 over x2 minus x1. Okay, so that is the y's over the x. So we see this, we are going upward, so the rise over run. Rise over run. Now let's assume we have these 2 points on this arc. We have these 2 points on this arc. If this is being expanded or zoomed out, we are going to have something like this. P here, and then this P, point P, and then point Q. So P here, and then Q also here. Now let this be again zoomed. So see something like P and then Q. If it's more zoomed out more, then we are going to see something like P here and then Q somewhere here. So as the points are being stretched, as P and Q are being stretched, we'll see P and Q from here to be more of P somewhere here and then Q somewhere here. And then we are told to find the gradients of the point of the line joining these 2 points. So let me draw a straight line from here joining Q. Now I'm going to find the slope of the line joining P and Q. The points P and Q has been drawn on the Cartesian plane. Okay, so I've called this the point P, the x component here x, and then the y component here f of x. Okay, so and I've named the arc y equals f of x. Okay, so the first point here is x for the point P. Then the first of the y-axis is also, so let me name my axis. So it's also f of x. Okay, so the point is x, comma, f of x. Okay, now from here to here, there has been some change. From here, from this point to this point, there has been some change. So let me call that change del x. Del x. Okay, so from here to here, x plus the change becomes x plus the change del x. So I said I'm going to call the change del x. So it's like when you're moving from 1 to 2. when we move from 1 to 2, there has been another addition 1. Then you go to 2. Okay. Okay, then again, on the y-axis, this f of x from here to here has also been a change del x. I'm going to call that change del x from here to here. So it makes the point q, the x components in q, x plus del x, because there has been the change we talked about here. So x plus del x. Then the component of y becomes f of x plus del x. So that is f of x plus del x, because from f of x to this point, there has been a change, which is del x. Okay. Now, let's find the gradients of the point, the line joining these 2 points. So I'm going to call the gradient m, which is equal to, and let's go back to where we started. We said the gradient of the line joining 2 points is given as y2 minus y1 over x2 minus x1. So this is the idea we are going to use to find the gradients of the line joining the points Q, P and Q. Okay, so from here, my y1 is f of x. So this is the first point. So y1 is f of x. And then my y2 is also f of x plus del x. Okay, then my x1 is what? X. Then my x2 is x plus del x. So now I can use this to find the gradients of the line joining these 2 points. So in this case, my m is equal to y2, which is f of x plus del x, minus y1, which is f of x, over my x2, which is x plus del x, minus x1, which is x. Okay, so this is what we have now. Now here we can simplify this. So f of x plus del x minus f of x over, so we see this is x, then minus x. So this x will take care of this one, because that would be 0. So we're left with del x. Okay, so it means that my m is now f of x plus del x minus f of x all over del x. Okay, so all over del x. Okay, so from here, my m, which is the same as changing, I'm going to call the change dy, that is rise over run, dx. So dx, and that is equal to f of x plus del x minus f of x all over del x. Okay, now if I am told to find the limits of this gradients, so that is going to be the limits as del x approaches 0, as del x approaches 0 of this one. So the limits of m, which is equal to f of x plus del h minus f of x all over del x, will be m equals the limits as x approaches, or as del x approaches 0. So f of x plus del x minus f of x all over del x. Okay, so let me indicate this, or change this to dy dx. That is change in y over change in x. So m is now equal to dy dx, which is equal to the limits as del x approaches 0 of f of x plus del x minus f of x all over del x. So from here, let's del x be h. So when we see the x, we put h there. So therefore, my dy dx, which is the same as this m, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now we talk of this as the first differentiation from the first principle. Differentiation from the first principle. Please don't forget to subscribe, like, and share this channel. The name has always been Odu Maths. Please comment as well. All comments are welcome. Thank you.